Non-destructive testing. Ultrasonic examination. The basic principle of ultrasonic testing of materials is the propagation and reflection of sound waves. As an example, a cylindrical workpiece is shown in the animation. The longitudinal section through the cylinder shows the position of the atoms extremely magnified and simplified as a single crystal. To begin with, a rigid unyielding stop is attached to the right front end of the cylinder. At the left front end, a disc is installed. It will be used to transmit and receive sound waves. Pushing and pulling briefly at the disc causes a longitudinal sound wave to propagate through the cylinder. When the sound wave reaches the rigid stop at the right side, it is reflected and runs back towards the disc, which now serves as a receiver. A free end is also able to reflect a wave. In this case, however, the tensile side runs ahead in the reflected wave and finally deflects the receiver to the right. The reflected wave is even reflected again and actually travels for several times across the length of the cylinder, but this is not shown in the animation for the sake of simplicity. So, if a sound wave is generated at one end of a workpiece, it will travel through the material with its speed of sound. At the free end of the workpiece, the sound wave is reflected and it returns to the transmitter, which then acts as a receiver. For ultrasonic testing of a workpiece, not a large transmitter is used in most cases, but a rather compact one, which generates a short ultrasonic pulse. At a place free from defects, the ultrasonic pulse travels to the right front end, also termed back wall. The pulse is reflected and recorded again as an echo. When the transmitter is moved a little downwards, the cavity reflects a part of the wave. That part arrives earlier at the transmitter than the rest of the sound wave. Even further downwards, the cavity reflects the complete ultrasonic pulse. For material testing, either the echo of a defect can be utilized, this is the pulse echo mode, or the phenomenon that hardly any sound waves pass through the imperfection. This is called the through transmission mode. In pulse echo mode, a transducer installed in a probe performs both the sending and the receiving of the ultrasonic pulse. On a computer monitor, the intensity is being plotted upwards on the y-axis and the time towards the right on the x-axis. With the probe at a place free from defects, only two signals may be seen on the monitor: the transmission pulse and the echo resulting from the lower surface of the workpiece, termed back wall echo. Moving the probe towards the right leads to an additional echo created by the defect. Even further towards the right, only the defect echo is visible apart from the transmission pulse.
Test of piezoelectric ceramics for cracks detection. The objective of this video is to present step-by-step a test methodology for cracks detection in piezoelectric ceramics used in ultrasonic power transducers and converters. The test is convenient and fast, and allows the quality control of new and used piezoelectric ceramics. Just use the TRZ transducer and horn analyzer and its software. The software allows to detect low amplitude disturbances in the measurement, which indicates the presence of cracks in the ceramic. Now we will show step by step how to test the ceramics for cracks detection. Step 1. Use the TRZ analyzer and configure its software for pieces. Step 2. Connect the piezo holder on the TRZ. Next, place the ceramic on the piezo holder. Step 3. Perform the measurement by clicking the play button, and then wait for the measurement. The intact ceramics do exhibit well-defined resonances. Ceramics with cracks or microcracks exhibit spurious resonances, which leads to low amplitude disturbances in the graphic. The ceramics with cracks or microcracks, even if invisible, should be rejected and discarded.